Good morning, students. In today's lecture, we will discuss Schur's lemma and semi-simple modules. So, first of all, we discuss Schur's lemma. The statement of this lemma is M and N are two R modules, and we have a non-zero homomorphism from module M into the module N. And we are to prove that if the module M that is simple, in that case this homomorphism is 1 1. And if N is simple R module, then F is onto. And if M is simple R module, in that case the set of all the endomorphisms of the module M, that is a division ring. So we'll discuss these three parts one by one. So first part. In the first part, we are given that M is simple R module, and we are to prove that F is 1 1. In order to prove that F is 1 1, let us prove that the kernel of the homomorphism that is 0. So we have denoted X is the kernel of the homomorphism F. Now by definition, the kernel of the homomorphism, that is a submodule of M. So we can say X is a submodule of M. Now, because we are given that F is non-zero homomorphism, so we can say that the kernel of this homomorphism will not be equal to M. Because if the kernel of the homomorphism that will be M, then the image of all the elements of M under F, that will be 0. So by definition, in that case, F will become 0 homomorphism, and we will get a contradiction in that case. So we can say that kernel is not equal to M. Now, because kernel of F, that is a submodule of M, and this is not equal to M. And here we are given M is simple R module, and a simple R module that has only two submodules, either 0 or M. So here X can take only two values, either it is 0 module or it is equal to M. But here, because X is not equal to M, so we are left only with one possibility. It means X should be 0 module. So we have proved kernel of the homomorphism F, that is 0. So by definition, we can say that mapping F, that is 1 1. So we have proved if M is simple R module, in that case F is 1 1. Now we discuss the second part. In the second part, we are given that N is simple R module, and we are to prove that F is epimorphism, means F is onto. In order to prove that F is onto, we are to prove that the range of homomorphism F, that is equal to N. So let us take the range of mapping F, we have denoted by Y. And by definition, the range of homomorphism, that is a submodule of N. And here, because F is non-zero homomorphism, so Y will be not equal to 0 module. Now, because N is simple, so it has only two submodules. So either that will be 0 or is equal to N. And here, because Y is not equal to 0 module, so Y will be is equal to N. And Y is the range of homomorphism F. And because range of homomorphism F is equal to N, so by definition F is onto. Now we'll prove the third part. In the third part, we are given that M is simple R module, and we are to prove that the set of endomorphisms of M, that is a division ring. We already proved that the set of endomorphisms of M, that is a ring under the binary operation F plus G of X is equal to F of X plus G of X. Here X belongs to M, and f and g are the endomorphisms of M. And second operation, image of x under fg is equal to f of g of x. Under these two operations, the set of endomorphisms that becomes a ring, and also the zero mapping from M into M, that is the additive identity of this ring, and the identity element I from M into M, that is defined by the image of every element of X. Image of every element of M under this mapping is X. The mapping defined in this way, that is the identity element for this ring. So, in order to prove that this is endomorphism ring, it remains to prove that every non-zero element of this ring has multiplicative inverse. So, let us take a non-zero element f belonging to this ring of endomorphisms, and we have denoted it by f. It means f is a non-zero endomorphism of M. Now, in the first part, we have proved that if M is simple, then the mapping is 1, 1. So, here because we are given M is simple, so F is 1, 1 by the first case. From the second case, if this is simple, then mapping is onto. So, by using the second part, we can say that F is onto. So, we have proved F is 1, 1 as well as onto. And therefore we can say that F is invertible, and F inverse, that will also be an automorphism of M. And so by definition we can say that the ring of endomorphisms of M, that is a division ring. So this completes the proof of Schur's lemma, and this is an important lemma. This completes the topic simple modules. Now we will discuss what are semi-simple modules. So definition is, what is semi-simple R module? And it is also called completely reducible R module. So let us take M be a module over the ring R. Then we say that M is completely reducible, or M is semi-simple R module if it can be written as the sum of simple submodules. It means if there exists a family which we have denoted by the collection M lambda, where lambda belongs to the uppercase lambda. This is a family of simple R submodules of M, such that M can be written as the sum of the members from this family. So if this condition holds, we say that M is semi-simple R module. The basic example of semi-simple R module is a module over a field. Module over a field means vector space. So that is an example of semi-simple module. Now next we discuss an important theorem based on semi-simple modules. So the theorem is, let M lambda, where lambda belongs to uppercase lambda, this is the family of indexes from which we are having the indexes. So this is the family of simple R submodules of an R module M, such that M is summation M lambda. Lambda belongs to this family of indexes, which is uppercase lambda. It means M is semi-simple. N is some module of M. Then we are to prove that there exists a subset of this uppercase lambda family, such that M can be written as N direct sum summation M lambda, where lambda belongs to this subset. This is the definition of, in terms of direct summand, we can give the another statement of this theorem. First of all, we discuss what is direct summand. Let us take M is a module and N is a submodule of M. Then we say that N is direct summand of M if there exists a sum module n dash of m such that m can be written as n direct sum n dash. So in terms of this definition, this statement can be written as, here n is direct summand of m because this will be a sum module of m, which is existing sum module. So in terms of direct summand, we can rewrite the statement of this theorem that every sum module of completely reducible R module is a direct summand. So here we are proving that n is the direct summand of m. Now to prove this, let us take the family which is denoted by uppercase lambda. Let us take this family is non-empty, because if the family is empty, in that case the result trivially holds. So we'll discuss the case when this family is non-empty. If n is equal to m, in that case we can write it again as m is equal to n plus 0 module, and this can further be written in this form. So in this case we can say m is equal to n direct sum summation m lambda, where lambda belongs to this family. This family here can be taken as empty family. So if m is equal to n, in that case our result holds. So now we will discuss the case when this family is non-empty and n is not equal to m. Now here we have taken n is not equal to m. Now because n is a sum module of m and n is not equal to m, so we can say that n is properly contained in m. And because we are given m is equal to summation m lambda, where lambda belongs to the family of indexes, so there will exist a suffix lambda naught belonging to the family of indexes such that the member m lambda naught corresponding to this suffix, that will not be contained in n, because if all the m lambdas are contained in n, then m will be contained in n and n is also contained in m. So m and n will become same in that case. But we are having n is not equal to m. So we can say that there will exist a suffix lambda naught belonging to the family of indexes such that m lambda naught will not be contained in n. Now, intersection of two sum modules m lambda naught and n. This intersection, that is a sum module of m lambda naught, and m lambda naught is simple, and simple module has only two sum modules, either 0 or itself. So either this intersection will be 0 module or either this intersection will be m lambda naught. If this intersection is equal to m lambda naught, then what will happen? M lambda naught will be contained in n, which will again be a contradiction. So we are left with this possibility only. It means m lambda naught intersection n, that is 0 module, and therefore their linear sum, that will be same as their direct sum. So if we consider the family consisting of this suffix lambda naught, then we have proved that n plus summation m lambda, where lambda belongs to this family, that is equal to n direct sum of summation m lambda, where lambda belongs to the family uppercase lambda naught. Now, in order to prove the theorem, we will use John's lemma. John's lemma we have already discussed in the topology also. So to use John's lemma, first of all we will have to define a partially ordered set. We will take chain in that set, then we'll find the upper bound, and if the chain will have upper bound, then the partially ordered set, that will has a maximal element. So in order to use John's lemma, first of all let us define a set and a partial ordering relation on that set, so that becomes partially ordered set. So let us define a collection tau. This is a collection of all those subsets of the family which is denoted by uppercase lambda, such that n, the sum of n with summation m lambda is equal to n direct sum of summation m lambda, where lambda belongs to this family. Then we can say that this family is non-empty family from here. Now let us define a relation on this set so that it becomes a partially ordered set. So the relation we have denoted by this sign, greater than or equal to. Let us define this relation. Let us take two members belonging to this family. We say that the member lambda 2, that is related to lambda 1 if the family lambda 1 is contained in lambda 2. This is the symbol for uppercase lambda. This relation is a partial ordering relation in tau. So this will become partially ordered set. Now let us take C is the chain in this set. The members of the chain we have denoted by lambda i's. So by definition of these members, because these are belonging to tau, so by definition of this family tau, the linear sum of n and summation m lambda, that will be same as n direct sum summation m lambda, where lambdas belongs to these lambda i's. Now let us take lambda dash, that is the union of these lambda i's. Then we claim that this is a member of tau, and this will be an upper bound for the chain. So for this, in order to prove that this is a member of tau, we will have to prove that the linear sum of n with summation m lambda is equal to n direct sum summation m lambda. To prove this, let us take an arbitrary element belonging to this sum. Now by definition of linear sum, z can be written as one element from n, which we have taken as x, and one element from summation m lambda, which we have taken as y. Now because y belongs to summation m lambda, where lambda belongs to lambda dash, so by definition y will be finite sum of elements of m lambdas, where lambdas belongs to this family lambda dash. And what is lambda dash? That is the union of lambda i's, and because lambda i's, they are the members of chain C, and by definition of chain, the elements of chain are comparable. So we can suppose that y is the finite sum of the elements from m lambdas, where lambdas belongs to lambda i's. So we can say that z belongs to the sum of n and summation m lambdas, where lambdas belongs to lambda i's, and this sum is equal to n direct sum summation m lambda, where lambdas belongs to lambda i's. So this representation of z, that is unique. So the sum, linear sum, that will become direct sum, and therefore we can say that the suffix lambda dash, that will belongs to the family tau. And also by definition, lambda dash, that is the union of lambda i's, and therefore lambda dash, that will be related to lambda I for every I belonging to index set. So by definition we can see that lambda dash is upper bound for the chain. Now we are in a position to apply John's lemma. So by John's lemma, this family which is partially ordered set tau, that will have a maximal element. So let us take the maximal element of this partially ordered set is lambda dash. Now by definition of this family is having all those subsets of lambda for which the linear sum of n with summation m lambda is equal to n direct sum summation m lambda. Here lambda belongs to the set lambda dash. Now let us turn towards our main result. we are to prove that n, the sum of n with summation m lambda, that is equal to m. To prove this, let us denote this sum by m dash. Now m lambdas are sum modules of m, n is also sum module of m, and the sum of sum modules is again a sum module of m. So m dash is a sum module of m. Now we are to prove that m dash is same as m. We prove it by contradiction. Let us assume m dash is not equal to m. If m dash is not equal to m, that will be properly contained in m. Now, as in the first step of the theorem, we proved in the same way, here we can prove because m is summation m lambda and m dash is properly contained in m. So there will exist a suffix belonging to the uppercase lambda family such that m lambda dash will not be contained in m dash, because if every m lambda that is contained in m dash, in that case m will be is equal to m dash, but here m and m dash are not equal, and therefore we must have in this case the linear sum of m dash with m lambda dash will be same as their direct sum, because in this case the intersection of m dash with m lambda dash, that is 0. So this sum in this case becomes direct sum. Now let us define the another family lambda double dash by joining this member lambda dash to the family uppercase lambda dash. Now let us again find the sum of m dash and m lambda dash. Now from here this sum is equal to the direct sum, and again we can put the value of m dash, putting the value of m dash here, and this can again be written as n direct sum, and this can further be written as direct sum summation m lambda. Lambda belongs to the family lambda double dash, because lambda double dash is the family consisting of uppercase lambda dash union lowercase lambda dash. So if we combine these two, we get this family. So because here this linear sum is equal to direct sum, and by definition of family tau, we can say that this lambda double dash that belongs to the partially ordered set tau, but that will give us a contradiction, because we have already proved that this uppercase lambda dash, that is the maximal element, and here we have obtained contradiction to the maximality of lambda dash. So this contradiction proves that our assumption is wrong. It means m and m dash, they must be same. Now we can put the value of m dash which we defined. So m is equal to n, the sum of n with summation m lambda, where lambda belongs to lambda dash. So we have proved the result here from the equation second. We have obtained m is equal to n direct sum summation m lambda, where lambda belongs to the family lambda dash. Let us denote this module by n dash. So we can write m is equal to n direct sum n dash, and by definition of direct summand, we can say that n is direct summand of m. So this completes the proof of this theorem.